This is lecture 15 on urban transportation planning. We will continue our discussion on modal split analysis in this lecture. Let us first recall what we discussed in the previous lecture. First, we started our discussion on earlier modal split models with specific reference to trip interchange type modal split model, and we discussed about the involved variables in the model, and finally looked at the characteristics of the model by referring to a graph involving all the variables including the socioeconomic characteristics of the urban dwellers. Then we discussed about disaggregate type of mode choice modeling, and under that title we discussed about the importance of disaggregation in mode choice modeling. The reason being, every individual is going to be different in their own way while choosing mode for travel. So it is very difficult to assume that everyone will choose a particular mode based on the modal attributes or based on the values commonly assigned for the modal attributes. That is the reason why it was felt to be more appropriate to go in for disaggregate modeling of mode choice. Under this topic we discussed about utility function, development of utility function involving a set of modal attributes, and we were specifically talking about mode specific type of utility functions, utility function developed for each of the alternative modes, or rather separate utility functions developed for each of the alternatives involved in the transportation system. With this briefing, let us try to specifically capture some of the important points of the previous lecture by answering the following questions. Question number 1 is this: list the set of variables used in the trip interchange type of mode choice model. Any response? Let me just give you the answer for this question. You may recall we discussed about travel time ratio, travel cost ratio, travel service ratio, and then 3 categories of socioeconomic groups of travelers, namely low income, middle income and high income groups. So these are nothing but the variables involved in this particular type of model, isn't it? We just express the variables in the form of ratios because there were only 2 modes involved in the mode choice analysis. That is how we need to understand the answer for this particular question. The second question is this: list the drawbacks of the earlier mode choice models. Disadvantages, drawbacks of earlier mode choice models. We found that there were 2 drawbacks of earlier mode choice models. The first one was that the captive travelers were not segregated from the database. The model represented both choice as well as captive riders. That is how the model need not be a very accurate representation of reality. And second limitation or drawback is that zonal aggregate values were considered for modeling. When you consider zonal aggregate values, it indirectly implies that an assumption that every household in a zone will behave in a similar manner under a given choice situation is already made, which is not correct. In reality, households and individuals may differ in their perception of the level of service offered by different alternative modes, and their choice process need not strictly be based on the calculations made using the zonal average data. So, these are the two drawbacks of this particular model. Third question is this: what is the basis for the methodology used in disaggregate mode choice modeling? Basis or the theory behind disaggregate mode choice model.
The utility of the particular mode which is being used by the travelers, that is the basis for this disaggregate modeling.
The basis is the discrete choice theory, or the utility theory is a basis for this particular approach for modeling, right. I suggest that all of you try to recollect what we discussed in the previous class, so that you feel at home when we proceed further. The last question: list the modal attributes used to formulate utility functions. We have seen utility functions for a set of 3 modes in the previous class. What were the attributes used to develop utility function? Attributes are nothing but modal characteristics which are considered as causal variables in the mode choice process. Any response? On what basis people choose modes? Based on travel cost, travel time, travel comfort, and so on. These are the attributes, right, used in the development of utility function. Very simple, nothing complicated. Clear? So, with this understanding, let us proceed further to see whether these mode specific utility functions were all right or there were some problems. As stated here, although there may be some validity in the mode specific approach, it causes a problem when a new mode is introduced, as I pointed out in the previous class. What is the problem? Calibration of the utility function may not be possible because we will not have any database for calibrating the utility function for the new mode as per the mode specific approach. So, that is a real problem, and this problem was proposed to be solved by Lancaster, and based on choice abstract or attribute specific approach. It is not specific to mode, it is going to be specific to attributes, modal attributes. That is the approach proposed by Lancaster. Let us see how to go about developing utility function based on modal attributes alone to cover all modes. The choice abstract theory is based on the hypothesis that when making choices, people perceive goods and services in general, goods and services indirectly in terms of their attributes, each of which is weighted identically across choices. They look at the attributes only, not the make or brand or something else related to the alternative modes. Let us say there are 2 service providers for cell phone, BSNL and Airtel. What are the attributes that influence choice of these services? The basic attributes are
network coverage
or effectiveness of the coverage,
cost per call,
cost per unit time, maybe cost per minute. These are the 2 attributes, and we look at these attributes in isolation, just we compare the cost per unit time and then effectiveness of the coverage, and if it is same in both the cases, for a user both are same, or if there is a difference in these attributes, then that particular service is taken for utilization or use, right. So it is based on attributes, not based on specific alternatives available. You have different brands of cars available in the market: Maruti Suzuki, Hyundai, Tata. Let us say we fix a set of attributes for choice of a car for our use. First attribute, let us say the size of the engine. You want to have 1.2 liter size of engine for your use. If all the makes have 1.2 liter size, you do not distinguish between the 3 makes, all the makes are same for you. The wheel size, if you prefer a particular size, say 14 inches, if all the 3 makes have the same size, you do not differentiate between the alternatives. The trunk size, if it is same for all the 3 makes, no difference as far as the user is concerned. The headroom inside the vehicle, if it is going to be same for all the cases, then there is no difference. So you perceive the utility of alternatives based on a set of attributes and assign same weightage, or in other words, you do not differentiate between 1.2 liter engine of Tata and 1.2 liter engine of Hyundai, even though there could be some differences. For choice purpose, you treat both these makes to be same because that attribute is same. That is the assumption made in this particular theory. I will repeat again, the choice abstract theory is based on the hypothesis that when making choices, people perceive goods and services indirectly, not by making use of each alternative service, indirectly in terms of their attributes, each of which is weighted identically across choices, right. It is attribute based approach. Thus, trip makers perceive 2 distinct modes offering the same cost, level of service and convenience as being identical, no difference at all. Continuing with the 3 mode example that we have seen earlier, a mode abstract model of modal choice would be a just single equation to measure utility, is not it. When we just consider only the attributes, there is no need to have specific equations for each of the alternatives, we can have single equation. So this will be the utility function even when you have 3 alternative for choice. You may wonder, then how do we get different utility values for the 3 alternatives? How the V value is going to be different for the 3 alternatives? It cannot be exactly same, is not it. In practice there will be some difference. How do we get the difference? Obviously we will collect information about the values of x1, x2 and x3 for these alternatives. So the values of these variables will make a difference in the value of V, is not it. So ultimately the V is nothing but the cumulative effect of the 3 attributes, namely x1, x2 and x3. Even though coefficients are same, the values of x1, x2, x3 is going to make a difference. So differences in the utilities, namely V, associated with each of the competing modes arise because of differences in the magnitudes of the attributes x of these modes. That is how you are likely to get different V values for different alternatives. this approach is not completely okay. Though the attribute specific approach has a strong conceptual foundation, in practical applications it is not possible to enumerate all the relevant attributes involved in the choice of mode, or it is not possible to take into account all the attributes accounting for the total utility of a mode. We just consider 2-3 attributes and quantify the utility. There could be unaccounted part of utility associated with each of the alternative modes, and that unaccounted part may make a significant difference in the total utility of the alternatives, isn't it, based on which we make normally choices. In this equation, where is the unaccounted part indicated? Is there any indication about the unaccounted part? The constant term 3.1 is the portion which is not accounted for by any of the variables or any of the attributes. So this is a single constant value given for all the 3 alternative modes. The question is it right to assume that the unaccounted part is same for all the 3 alternatives? It is not right. It will be different for different alternatives. The level of service provided by mode 1 may be explained by x1, x2 and x3 to an extent of 95%, and the total level of service offered by mode 2 may be explained by these 3 variables x1, x2 and x3 to an extent of only 88%, isn't it? So it is not right to assume that the number indicated as a constant term is same for all the alternatives. So we must do something about it. How to do some compensatory measure for this particular problem? The first constant term in equation 3 is meant to capture the effect of variables, as I said, that are not explicitly included in the model. It is unlikely that a given set of competing modes will be identical in these excluded attributes. That is what we discussed. Need not be identical, there will be variation. Hence, it is reasonable to attempt to capture these unexpressed differences by calibrating for alternative specific constants, or in other words, by some means, if it is possible for us to get different constant values for different alternative modes, it will be more appropriate and we will be able to get more accurate and representative value of V as total utility of various alternatives instead of having only one constant term. And this can be done by taking one mode as the base mode. This can be done by weighting the explicitly identified attributes equally across modes by utilizing any of the modes in the choice set as a base mode. You consider one mode as a reference mode and look at the constant term for that mode and express the relative constant terms for other modes in relation to this constant term, so that your comparison is more effective, right. Thus in equation 2, which we have seen in the last class, for the benefit of recollecting what we did, I will just show you the 3 equation. This is what we saw under mode specific case, 3 utility functions for 3 alternative modes, right. Look at the constant terms. For V1 it is 6.2, for V2 3.4, for V3 it is 4.3. Now the question is, can we just modify these constant terms in relation to a base mode? let us say we take mode 2 for which utility value is V2 as the base mode, and subtract the value of the constant term pertaining to that mode from all the constant terms, for example. Then for V2 the constant term will become, no, for V2 we are subtracting the value, it will be 0, and for other modes, for V1 it will be 6.2 minus 3.4, for V3 it will be 4.3 minus 3.4, right. So that there is some relationship between the unexplained part between the three alternatives. That is what we want. We are not interested in the absolute value, but the difference is more important. That gives you a correct picture to enable the travelers to choose a particular mode based on the bundle of the attribute values of the modes. So that is what is indicated here. Thus in equation 2, 2a, 2b and 2c, instead of having a1 to be equal to 6.2, a2 being 3.4 and a3 being 4.3, the model may be estimated with mode 2 as a base. Then the alternative specific coefficients would be a1 will be simply 2.8, a2 0 and a3 0.9. Clear? So this is how we can get over this particular problem of unexplained part of the utility of the various alternative modes with the available attributes that we make use of to develop the utility function. Clear? So this problem can be sorted out to some extent. Then you can write the general form of the utility function like this. The calibrated utility function in the case of the 3 mode example may then become simply Vk. We are not making it specific to a particular mode, just mode k to be equal to Ak. Ak can take a value depending upon the mode under consideration, Ak plus then 2.5 x1 plus 1.5 x2 plus 0.8 x3. These numbers are based on some calibration. Let us not worry about these numbers. General formulation is important. We do not give specific number for the constant term. It will attain or take a corresponding value based on the mode you consider to develop the utility function, right. Where Vk is the utility of mode k and Ak is the calibrated mode specific constant for the same mode, which represents the fixed advantage or disadvantage of mode k vis-a-vis the base mode. That is our interest. We consider one mode as a base mode, with respect to that whether the other mode has got an advantage or disadvantage can be easily assessed by this approach. They are clear. Now it is not the end of the story. Although the attribute specific utility function shown in the previous equation is conceptually convenient, we have single equation, we managed to solve the problem of the constant term, but still there are some problems when we use these utility functions in practice. Practical problems often call for a mixed form that includes both attribute specific and choice specific terms. There may be certain situation where you may have to necessarily bring in some mode specific attributes in addition to accounting for a set of common attributes for all the alternatives. In a specific case it may be necessary for us to introduce another attribute specific to a particular mode. The example is this: the need to capture the added utility of using transit for travel oriented toward the central business district is one example. Why this is given as an example? how there is added utility for the transit when the travel is towards CBD. CBD is city center where most of the activities are concentrated. So, people travel to city center, the movement is going to be towards city center in the morning peak and then away from city center in the evening peaks. That will be the normal travel pattern. But here it has been mentioned that utility of transit is going to be more compared to the private transport vehicle when the trip is oriented towards CBD. Even though this statement may not be very accurate for the conditions prevailing in developing countries. In developed countries, there is a lot of restriction with regard to parking facility in central business district area. Limited parking facilities and parking fee is very high to discourage car users to bring their car to the CBD area to reduce congestion. Then obviously transit becomes a preferred mode, there is a specific advantage. So, this is one situation. In another case, people might be travelling in the peripheral areas from an origin to a destination. There you will find that both the modes might be equally competing, or maybe car has got an advantage over transit, possibly because of lesser frequency service in the peripheral areas with transit service, right. So, it is specific to a particular travel pattern. If the trips are considered connecting the CBD and other activity centers, then we need to introduce some other factor to take care of the advantage enjoyed by transit when one trip end is connected to CBD. Otherwise, if we simply use the utility functions commonly derived taking into account the data covering the whole of the urban area, it may not work for trips made towards and away from CBD. If one trip end is connected to CBD, then we would have missed this particular aspect of transit enjoying better patronage compared to car. So, how to bring in this situation in the modeling process? It is possible, and we need to do this by some methodology. The effect of this attribute is usually positive, obviously for the transit, adds utility or reduces disutility for transit because of the limited availability and high cost of parking at the CBD destination for private vehicles. This is a solution. A binary variable taking the value of a 0 for non-CBD orientation and 1 for CBD destination trips may be included along with its coefficient in the transit utility equation. You introduce a binary variable which is also termed as a dummy variable by some authors, right, to distinguish between transit and other alternative modes. So, this variable will take a value 1 if the trip is towards CBD and 0 if it is non-CBD oriented trip. So, whenever you deal with CBD oriented trip, there will be some weightage added to the utility of this particular mode and 0 weightage if it is concerned with trips not connected with CBD. So, this technique of modeling is also called as a dummy variables technique. This variable will have just only 2 values, 0, either 0 or 1, but still it will be introduced as a variable and there will be a parameter coefficient for this variable also when you develop equation by regression technique. This is a situation that arises quite often in modeling process. You take the case of mode choice by younger people and elderly people, aged people above 70 years and below 70 years. The physical constraint of elderly people excludes some of the alternatives from their choice set, isn't it? They will not be able to drive on their own, right, or some public transit modes may not be easily accessible to them, right. The floor level of some of the buses are too high for them to climb up. So their constraints with regard to mode choice is going to be totally different from the mode choice process by others. But when we do mode choice modeling, we include all kinds of travelers including elders, right. Then how do we explain choice of mode by elderly people? You must first distinguish the travelers based on age, whether they are 70 plus or less than 70, right. If they are 70 plus, give the binary number value 1, less than 70 is 0, right. Use dummy variable technique in such cases, still bringing these variations in your modeling process, right. So these are all the techniques quite commonly used in any choice process, not only in mode choice. You have to differentiate situations based on the field conditions. The inclusion of variables describing the demographic and socio-economic characteristics of trip makers in a utility function brings to bear another consideration. So far we have been discussing based on the assumption that there is no distinction between individuals. We have not considered socio-economic characteristics of people in our discussion so far in the mode choice modeling or in the development of utility function. We consider only modal attributes x1, x2, x3, whatever we considered were modal attributes. So it is appropriate to bring in the socio-economic characteristics of travelers into your choice process, so that your model really reflects the actual choice process. Now the question is, how do you bring in socio-economic characteristics of travelers in the mode choice process? Anyway, one important characteristic which needs to be brought in is the economic status of a traveler. A rich person, a very rich person may never choose a transit, they might be using their personal vehicle. A very poor person may always use only transit, isn't it? You cannot treat all the travelers to be same for mode choice modeling purpose. Somehow we need to bring in the economic status in the development of utility function. Any suggestion? It should be based on the extent of pinch of purse they feel while spending money for making trips, right. A middle class person may spend a lot of money in his perception for travel. A rich person may be spending a small proportion of the total income in transportation, isn't it? It depends on the pinch the purse realizes for different individuals in making trips. Okay. The cost is not same for all individuals, even though absolute value is same, it is not going to be same for individuals. It depends on their economic status. Somehow you should be able to relate the actual transportation cost with the economic status of the travelers. How do we do that? Shall we express the cost of travel as a percentage of the monthly income? If there is some connectivity between the income of the traveler and the actual cost of transportation, then we will be able to bring in this particular aspect into our modeling process. Express the transportation cost as a percentage of the income of the travelers. You can broadly classify the travelers into high income, middle income, low income, like that, and get some ratio so that the economic status is automatically reflected when you develop utility functions. Since these attributes describe trip maker, they are the same for all choices or modes. the trip maker's choice set. Thus they do not differentiate in any way between choices. This has to be changed in fact, and for such characteristics to be sensitive to alternative choices, they must be included in the same term as model attribute. An example of this is the inclusion of an explanatory variable that represents the ratio of travel cost. Travel cost is a model attribute, is not it? Ratio of travel cost to the trip maker's income level. It is not absolute value of income, income level. You can broadly classify the income level into broader categories and incorporate that into your modeling process. A decision maker's attribute. It is to be noted that the said utility specification implies that all individual travelers in an origin zone I are represented by a typical or average traveler. There is another issue to be kept in mind. Even though we bring in the economic status of the traveler in the modeling, still we assume that if the traveler belongs to a particular income group, lives in a particular zone, then there is no difference in the mode choice process by any of the travelers within that zone within a particular income group. That is the assumption we are making so far in developing utility function. Will it be so in practice? You take a middle income group living in a particular area and they assess utility of different modes based on modal attributes as well as their income level. They perceive the utility of different modes. So far, based on the discussion, we can say that or we imply that all the travelers of a particular income group living in a particular zone will have same pattern of mode choice, isn't it? That is what we have been assuming so far in developing utility function, but in practice it need not necessarily be so. There will be difference in the perception of utility by different individuals, even though they might belong to same socio-economic group, same age, same income, right, same vehicle ownership, right, same social status. Still two individuals may not behave in the same way in choice of mode, and we need to somehow bring in this variation also into our modeling process. Otherwise we are not completely representing mode choice process, right. Let us see how to go about doing this. This assumption is clearly unrealistic, as I said, as the choice of mode by individuals depends on the relative utility of the mode as realized by him or her, as realized by him or her, it is very important, which depends on the characteristics of the individual and his or her perception of the utility of the chosen mode, perception of the utility. One may say bus is fine for me, other one would say bus is not that good, I prefer train. Third person might say bus, both bus and train are not good for me, I would just choose motorized two-wheeler. All the three people may belong to same age group, same income level, same social status, but still perceptions vary, and this has to be brought into our modeling process. Thus the moral of the story is this: the utility of a given mode is not a fixed quantity. You cannot just calculate the value of V and say this is the utility of a particular alternative mode. It is not a fixed quantity, but a random quantity as it varies between individuals. We need to treat V to be a random quantity, not a fixed quantity. Utility of a mode has to be treated as a random quantity. So bring in the theory of randomness into the mode choice process. Hence, the utility that a traveler in zone I receives when choosing alternative J can be written as the traveler lives in zone I and he or she is choosing alternative J, alternative mode J. This situation can be explained like this: Uij, utility of mode J for a traveler living in zone I, Uij is equal to Vij plus epsilon ij. Vij is known to us. Vij is nothing but the utility function about which we talked quite for some time, isn't it? We know what we mean by Vij. Vij value is obtained by calibrating an utility function involving the attributes of the alternative modes, right. And we are trying to introduce one more term, epsilon ij, and where Vij is the average traveller's utility. That is very important. Vij represents just the average traveller's utility. It is not bringing in the variation given by an utility function, and epsilon ij is equal to the uncertain or random part of the utility function specific to individual travelers. Now, the question is how to quantify epsilon ij and get the value of Uij, right. The key to the estimation of the probabilities of choice is to make specific assumptions about the probability distribution function of the random term epsilon ij. Our worry is to see how epsilon ij will vary, will get distributed, or is there a way to find out or formulate a probability distribution function for epsilon ij. I think you are familiar with different types of probability distribution functions, isn't it? Think about it, try to recollect. Those who are unable to connect yourself with the discussion, just to go back and refer the books and get connected to our discussion. Okay? Yes, could be either continuous or discrete, right. So, the key to the estimation of the probabilities of choice is to make specific assumption about the probability distribution function of the random term epsilon ij. There are suggestions available. If there are two alternatives, just to simplify the case, j to be equal to 1, 2 facing each individual traveler in a given zone I, then the corresponding random utilities for the two alternatives can be written as follows. It is very simple. Based on our earlier understanding, we can write utility of mode 1 is nothing but V1 plus epsilon 1. We are talking about travelers in a particular zone. So, I etc. is not brought in here because we talk about a specific case. So, you can write U1 to be V1 plus epsilon 1 for alternative 1, and U2 could be V2 plus epsilon 2, right. And if U1 is simply equal to V1 and U2 is simply equal to V2, then difference in utilities between the two modes can be easily calculated. Just a difference between V2 and V1 will give the difference in the utility of the two alternatives, but we have included a random term. So, unless the magnitude of epsilon 1 and epsilon 2 are known, we will not be able to really check whether mode 1 or mode 2 is going to be more useful to the travelers in a particular zone. The alternative that would be chosen by the traveler will now depend on the values of epsilon j, in this case epsilon 1 and epsilon 2 also, in addition to V1 and V2. Okay. The values of epsilon 1 and epsilon 2 will influence the choice of mode. That is how we need to understand the randomness in the choice process, right. The variation of the probability of choice of say alternative 2, let us say we are interested to know the probability of choice of alternative 2 as a function of the difference in systematic utilities, as a function of the difference in systematic or the constant or the average utility indicated by V, fixed part of the utility function, which is equal to V2 minus V1. Our interest is to find out the probability of choice of mode 2, that is why we have put V2 minus V1 here, right. Can be represented graphically as shown in the following figure. Let us try to represent the probability of choice of V2 for the given situation. This is how we can represent the probability of choice of V2. Study this plot very carefully. Probability of choice is indicated along this vertical axis, and difference in utility of the two modes is shown along the x axis. At this point both the modes have same utility, V2 is equal to V1. Known systematic utility or known constant value of or average utility is same in this particular case, whereas on the right side V2 is more than V1, on the left hand side V2 is less than V1. If the mode choice is going to be based only on the values of V, V1 and V2, obviously when V2 is equal to V1 it is likely that the division is 50% each, maybe half might choose V2 or mode 2 and half might choose mode 1, that is agreeable. But the point to be noted is when V2 is more than V1, when mode 2 is more useful than mode 1, as per the logic based on your constant utility, everybody should choose only mode 2, isn't it. But what is happening here, when V2 is more than V1, still there is increase in choice of V2, but not to the expected extent of everybody choosing V2, right. Even at this level of difference, you see only about 70 to 80% of the people choose V2 in spite of utility of mode 2 being very high, and still about 30% of the people are using mode 1 for reasons known to them based on their perception. And similarly when V2 is less than V1, obviously nobody should use V2 based on the value of V and everyone should use only V1, but it is not happening. Still some people are using V2, isn't it. Probability of choice of V2 is still there, and this explains the actual choice process. It is not strictly based on the systematic or the quantifiable part of the utility of the alternative modes. It is also dependent on the actual random part which belongs to or which can be explained only based on the nature of perception of the individuals, right. And this implies what? We can say that this is how the random term epsilon j varies, this is the effect of epsilon j, isn't it. That is what is plotted here. Effect of epsilon j is shown here, right. This has to be accounted for. Now the question is, what is the shape of this curve, and is it possible to standardize or at least associate this curve with known standard curves, is the question. And it was not that easy, a lot of research work has been done. It is clear from the figure that the probability of choice depends, in addition to the values of systematic utilities V1, V2, on the probabilistic nature of the random utility term epsilon j, that is what I told you. This leads to the issue of specifying probability distribution function for epsilon j. We need to specify a functional form for epsilon j, right. It has been found based on extensive research and considerations of simplicity. Extensive research leads to lot of complex conclusions also. So while you recommend something for adaptation, for implementation in practice, you need to think of simplicity in use of a concept or theory. Considerations of simplicity in analysis and possibility of getting closed form solution, that the Gumbel or double exponential distribution will be suited for fitting the random utility term epsilon j, that was a finding. So our subsequent discussions are going to be on the assumption that epsilon j will follow double exponential or Gumbel distribution, right. So with this let us recollect what we discussed in this class. We started our discussion on disaggregate mode choice modeling with the understanding of development of utility function specific to different alternative modes. But we realized later that mode specific utility functions will not be helpful, and we need to go in for attribute specific utility functions, because of the reason that mode specific functions will not be able to account for new modes that might be introduced in the future. So we realized attribute specific functions are much better than mode specific functions. In the attribute specific function, one aspect that we encountered was the constant term. So there was a need to take different constant terms for different alternatives to account for the variation in the utility of the alternative modes more accurately. And we know now that this can be achieved by taking one of the alternative modes as the base mode and vary the value of the constant terms. Even though this solves a problem and the attribute specific utility function could be a better tool for assessing the utility of alternative modes, there is a need to consider mode specific aspects on certain situations, like trips connected to CBD, where transit will have a specific advantage over personal vehicles. In that context, there is a need to introduce binary variable technique or dummy variable technique to take care of the CBD oriented and non CBD oriented trips. Then we found that it is also better to take socioeconomic characteristics of travelers in the modeling process to reflect the real choice process. We found that it is possible to take into account the economic status of travelers by expressing the cost of transportation as a percentage of the money income of the travelers. With this assumption or with this approach, we found that it is possible to satisfactorily develop utility function to assess the utility of different alternative modes. But still, one question which was not answered at that point of time was the variation in the perception of the travelers regarding choice of modes. This was not really brought into the picture at that point of time. So to bring in the individual variations in the choice of mode, the utility is treated as a random term, and instead of Vij we call it as Uij to be equal to Vij plus epsilon ij, where epsilon ij is a random part of the utility function which needs to be explained with reference to some random theory. Now finally we found, based on literature, that epsilon ij is distributed following Gumbel or double exponential distribution. So based on this assumption, we will continue our discussion in the next class to formulate more appropriate mode choice model to explain the choice process.